Hi dear all, welcome back to the class on rotational dynamics. The topic of today's discussion is the calculation of moments of inertia of some regular bodies. So for suppose we have for example some bodies like, say this is a uniform rod, then this is a ring like this. So in for such bodies we will be given some axis. If for example if I have a ring like this, I will be given an axis like this. So we will be required to find the moment of inertia of this ring about this axis. That means if the ring is rotating like this about this axis, if the ring is rotating like this, what is the moment of inertia of this ring about this axis? So such problems may arise. So in the case of some regular bodies, we have other bodies like, so we have some disc like this, then we have sphere like this. So for all these regular bodies, how will you calculate the moments of inertia of these regular bodies? So that is the topic of our discussion today. So initially, or as the first case, I have taken here the moment of inertia of a thin uniform rod. So like this, I have already shown you. This is a uniform rod, or if I am taking a uniform bar like this, and I am given an axis like this. Okay, this is a uniform rod or bar, and I am given an axis here. What is the peculiarity of this axis? This is an axis which is perpendicular to this rod and also passing through the center point, perpendicular to the length and passing through the center. So that is our first problem. So how will you calculate the moment of inertia of a thin uniform rod about an axis passing through its center and perpendicular to its length? So I have drawn here. So this bar is of length L. I have taken this bar is AB, length, total length L, and I have an axis passing through the center. How will you calculate the moment of inertia of this body? So that is our first problem. So going to that, so let PQ be an axis which is passing through the center of the rod. Then AB is the rod. The length of the rod is L. So since PQ is passing through the center, we know that this much length is L by 2 and this much length is L by 2. And also we will take that the total mass of this bar is capital M. So in order to determine the moment of inertia of this bar or rod about this axis, the first step is always like this. The first step is we will take mass per unit length of the rod. So that is the first step. So here we will take mass per unit length of the rod. We will take that to be m, small m, is equal to. So what will be the total mass? The total mass I have taken to be capital M. The total length is L. So I can write this m, that is mass per unit length. It is nothing but m, capital M divided by L. So this is for a uniform bar. That is why we have taken mass per unit length. Suppose it is for a disk. അപ്പോൾ നമ്മളൊരു ഡിസ്ക് ചെയ്യുവാണെങ്കിൽ the quantity that we will be taking first will be mass per unit area. Okay. When I take that portion, I will specify that. So when I am taking a uniform bar or uniform rod, I will be taking first the quantity which is mass per unit length. If I am taking a disk like this, I will be first writing the equation mass per unit area. Similarly, in the case of a sphere, if I am calculating the moment of inertia of this about some axis, the first quantity that I will take into my derivation will be the mass per unit volume. So there you can see, when we derive this, you can see that we will take the mass per unit volume. So here what we are taking first is the mass per unit length of the rod we have taken here. And for all these things, the next step is to consider a very small element. That means we know that this scale is made up of very small elements from here to here. So I will consider a very small element. So like this, I will consider a very small element here, like my finger. This is a small element. So this scale is made up of all such elements, right? Like that, it is joining up this element plus this element plus this element, like that. It continues from this end to this end to make the entire scale. So we are considering first. Then the second step is we are considering a small element of length. This is a small element that I am considering. Let this be of length dx. So as you know, in physics we always take dx for denoting some very small quantity, so dx, and let that element be at a distance x from the center. This is the center of the rod, that is O. Okay, so this element is at a distance x from the center of the rod. Then if the length of the element is dx, what will be the mass of the element? So our procedure is like this. We will first find, what we have to find out is the moment of inertia of this rod about this axis. First what we will do is we will find the moment of inertia of this small element about this axis. Okay, so moment of inertia of the small element will be derived first. The moment of inertia of the whole scale will be obtained. Integrate, because we know that the scale is made up of very small elements like this. Then we will integrate the expression. So what we are going to do first is we will determine the mass of the element. Then after finding the mass of this element, we will calculate the moment of inertia of this element about the axis PQ. Then we will integrate from a particular limit to another limit. So that is our procedure. So second step is the mass of this element. So what will be the mass of this element? We have calculated mass per unit length of the rod, we have written as m by L. So this is mass per unit length. The length of the element is dx. So what will be the total mass of that element? So that is our second step. Then mass of the element will be is equal to, what will be that? This into m dx. Okay, why? This is mass per unit length. Unit length in the mass on this scale in there. When we are considering unit length, it is m by L, and when we are considering a length dx, just multiply this by this. So that is what we are going to get, m dx. So now after getting the mass of the element, what is the next step? Next, what I want to write is the mi of the element, that is moment of inertia of the element of this length dx about PQ is equal to. So we have studied that the moment of inertia of a particle of mass m, like this. If I have a particle of mass m, this is an axis, for example, this is xy axis. This is the distance between this particle and the axis. We have already studied that this moment of inertia is given by mr squared. That is, moment of inertia is given by the product of mass of the particle and square of the distance between the particle and the axis. So similarly, I can consider that this element is at a distance x from O. So what will be this one? That will be m dx into x squared, right? Why? Because mass of the element is m dx multiplied by the square of the distance between the element and the axis. Okay, that is x. So now we have got the moment of inertia of the element about the axis PQ. So this can be written to be equal to mx squared dx. Okay. Now we have got the moment of inertia of the element about this PQ. Now we have to calculate the moment of inertia of the whole rod about PQ. Why will you do that? So for making determining that, we will assume that all such elements can lie between see that we have divided the scale into two parts. The scale is of total length L. We have taken this length to be L by 2, this length to be L by 2 because this PQ is at the center. Okay. So we can say that such elements can lie between. If I am taking the center part as 0, center portion as 0, this end is minus L by 2. Okay. Minus L by 2 is this one. This center portion is 0 and this is plus L by 2. So just like number line here is 0, minus L by 2, plus L by 2, like that. So these strips can lie here. Small strip can be here, here, like that, can come to center and from that. So the range over which these strips will be lying will be from minus L by 2 to plus L by 2, crossing this 0. So how will you integrate? In order to get the moment of inertia of the whole rod, what you have to do is you have to integrate this expression. Hope you are familiar with the process of integration. Integrate limit apply. Limit apply. You should apply limit from minus L by 2 to plus L by 2 because the scale is made up of all such small elements lying from minus L by 2 to plus L by 2. So what we can do is, therefore, elements can lie between minus L by 2 and plus L by 2. Okay. So making up the whole length of the scale. So I can write therefore mi of the rod about PQ is given by I is equal to, what you have to do is integrate, okay, minus L by 2 to plus L by 2 this quantity, that is mx squared dx. So how will you integrate this one? So you know that when you are integrating, m is a constant. Why? Because m is a constant means it is mass per unit length of the rod. Mass of the rod is a constant, length of the rod is a constant. So this m, which is m capital M divided by L, is a constant. It can be taken outside the integral. So I can write it here. I is equal to m into minus L by 2 to plus L by 2 of x squared dx. Okay. Then what is the integral of x squared dx? X squared dx in integral, as you know, it is x cube by 3. So I can write this one as m into x cube by 3, and you are applying limit minus L by 2 to plus L by 2. Okay. So this is what we are going to get. So we have m here taken out. X squared dx is x cube by 3. We will have to apply the limit minus L by 2 to plus L by 2. Okay. I is equal to m into x cube by 3. We are applying the limit minus L by 2 to plus L by 2. So how will you apply this limit? So it is like this, m into, you might be familiar with this one, m into, so this m is nothing but m by L. So I can write it here. Okay. I will write m is equal to m by L. Okay, I will write m by L, and there is a 3 coming here. I will take it out. M by 3L. Then I have taken these 3 out. So I have only x cube here. So instead of that x, I will first substitute L by 2, then minus L by 2. So what will you get? That is L by 2 plus L by 2 cube minus L by 2 cube. So this is how you apply limit. First apply upper limit, then apply lower limit. Applying upper limit minus lower limit. Okay. So this will be m by 3L into, this one will be, as you know, this one will be L cube by 2 cube. That will be L cube by 8 minus, this will be minus L cube by 8. So it will be plus L cube by 8. Okay. This will be m by 3L into L cube by 8 plus L cube by 8 will be 2 L cube by 8. So this will be L cube here, so it will be L squared here, and this is 3 to 8 24. This is 2 here, so it will cut, and finally I will get in the denominator 12. So finally what I am going to get is I is equal to ml squared by 12. So this is the moment of inertia of a rod about an axis which is perpendicular to its length and passing through the center. So if I have a rod like this which is rotating, I have rotating like this. The moment of inertia of about an axis which is perpendicular to it and passing through the center, the moment of inertia of this rod about this axis will be given by ml squared by 12. In that you have to remember that m is the mass of the scale, L is the length of the scale, 12 is a constant. So in problems you will be given a rod or a scale of mass some grams, then L some centimeter like that. In problem you will be asked, you find out the moment of inertia of this scale about an axis passing through the center. So immediately the formula should come to your mind, that is moment of inertia is given by ml squared by 12. Okay, so that is the first derivation. Then we can have some axis. Here we have taken an axis which is passing through the center. What about this moment of inertia of the same body if I am considering another axis? That is, I am considering an axis here. How will you calculate this one? This is where we apply the theorems that we have studied. We have studied two theorems, that is the theorem of parallel axis and also the theorem of perpendicular axis. Hope you remember that. So theorem of parallel axis and theorem of perpendicular axis. If I have an axis, I can find out the moment of inertia of the body about another axis which is parallel to it. If I know the moment of inertia of a body about an axis passing through the center, I can find out the moment of inertia of the same body about an axis which is parallel to this axis which is passing through the center. Using that principle of parallel axis, I can calculate the moment of inertia of this body if I am considering another axis passing through the end and the parallel axis theorem. So we are going to discuss that next. What will be the moment of inertia of the same rod about an axis passing through the end, perpendicular to the rod but passing through the end. This we have already found out. Next one will be the moment of inertia of this scale about this axis which is passing through the end. Okay. So the next part of the derivation is to find out the moment of inertia of the same rod but about an axis through one end and perpendicular to its length. So earlier we have determined this one. The moment of inertia of the rod about the axis passing through the center. Now we have given another axis which is passing through the end, one end. So suppose we have another axis here passing through the end, which I will designate as RS. So you know already PQ. What is PQ? The moment of inertia of this rod about this axis we have already derived, that is I is equal to ml squared by 12, that we have already derived. So this can be found out. Now about this axis RS which is passing through the end, that can be found out using the principle of parallel axis. What is principle of parallel axis? Principle of parallel axis, just to recollect what we have studied, I will write here. I have a body, I have an axis passing through the center of mass. If the moment of inertia of this body about this axis passing through the center of mass is I0. If I am considering another axis here, which is at a distance A from the axis through the center of mass, then if I is the moment of inertia of the body about this axis, this can be written. If I know this can be found out I0 plus m into a squared. What is m? M is the total mass of the body. So if I know the moment of inertia of the body about an axis passing through the center or center of mass, I can find out the moment of inertia about another axis if I know the distance between the two parallel axes. If I have a parallel axis which is there at a distance a, I can calculate this one from this one as I0 plus the product of mass and square of the distance between the two parallel axes. This principle we can make use of here. I already know the moment of inertia of this bar about this axis. To calculate this one, what I need is, I know this one plus m into a square, that mass of the scale. We already have taken it to be capital M, and the distance between these two parallel axes, that is this distance. What is this distance? We have already taken this to be L by 2, and this is L by 2. Now I can say that the distance between this axis and this axis is L by 2. Okay, so making use of that, I can write here, that is moment of inertia. So making use of this parallel axis theorem, moment of inertia of the rod about, or I will write here, moment of inertia of the rod about Rs is equal to this plus, that is moment of inertia of the rod about PQ plus M into, what is that, distance squared. The distance is L by 2, that is L by 2 the whole square. So this is, so moment of inertia of the rod about Rs, we can take it to be, okay, some I, okay, you can take it to be, so this can be taken to be I0, this is to be I is equal to moment of inertia of the rod about PQ is ml squared by 12 plus m into L by 2 the whole square. So this is being applied here. Okay, this is ml squared by 12 plus ml squared by 4. Okay, so that is equal to, so it will be this one, ml squared by 12 plus ml squared by 4 will be, we will take the LCM. So we have 12 4, what is that, 12. Okay, then 12 can be here, then this is ml squared plus this is 4 into 3, so 3 ml squared. So that will be ml squared plus 3 ml, so 4 ml squared by 12, that will be equal to ml squared by 3. So this is the expression for the moment of inertia of the rod about an axis which is perpendicular to its length and passing through the end. So we have problems like this. So now we have to be thorough with that. What is the moment of inertia of this bar about this axis? This is ml squared by 12. Okay. What is the moment of inertia of this bar about this axis? This is ml squared by 3, where m is the mass of the scale, L is the total length of the scale. Then what is the moment of inertia of the same scale about this axis? That is same as this one. Okay. Whether I am taking axis here or here, it will be the same one. So here it is ml squared by 3, ml squared by 12, ml squared by 3. Okay. So that the moment of inertia of this thin uniform rod is over. Now we will pass on to the moment of inertia of a thin ring. Ring means is something like this. Okay. Now the second body whose moment of inertia we are going to find out is a ring. Moment of inertia of a thin ring, or is it called a hoop, like just like this. And the axis that we are taking is an axis through its center and perpendicular to its plane. So what will be that axis? If I am having a ring like this, then the plane എന്ന് പറഞ്ഞാൽ ഇതാണ്. Okay, then the axis that we are taking will be like this. Okay, this is an axis. This is an axis which is perpendicular to its plane and passing perpendicular to its plane and passing through the center. അപ്പോൾ ഇങ്ങനെയാണ് നമ്മൾ കൺസിഡർ ചെയ്യുന്നത്. We have a ring here, we have an axis here about which is this is rotating. So what will be the moment of inertia of this ring about this axis passing through the center and perpendicular to its plane? അപ്പോൾ ഇവിടെ നമ്മൾ കൺസിഡർ ചെയ്യുന്നത് വെച്ചാൽ here also we are taking the axis to be PQ. for determining the moment of inertia of the ring about this axis, first of all, നമ്മൾ കഴിഞ്ഞ പ്രാവശ്യം ചെയ്ത പോലെ തന്നെ we are considering a small element of mass m here, small particle or small element of mass m here, and let r be the radius of this ring. Okay, so we are considering this particle of mass m or a small element of mass m which is at a distance of r from the center, because the r is the radius of this ring. Okay, എന്നിട്ട് നമ്മൾ എന്താ ചെയ്യുക, the first one will be mass of the element we have already taken, and the next step will be, what will be the step, we will calculate the mi of the particle about p2. So mi of this particle, or I will write it, mi of the particle means particle of mass m about p2 is equal to, we know that if I have a particle of mass m at a distance r from any axis, the moment of inertia of the particle is given by product of mass of the particle and square of the distance between particle and the axis. So I can write m r squared. Okay, m r squared. Now we will consider that we are consider now only one element here. ഇങ്ങനെ എത്ര എലിമെന്റ് ഉണ്ടാവും? So we can say that there are such elements here throughout this ring. Then if I am repeating this small element here like that, I will get the entire ring. So I can say that this ring is made up of all such elements from here to here. Then if I have got the moment of inertia of this particle about this one, how will I get the moment of inertia of the whole ring? Here there is no need for integration. And the other, why? Because when we considered a bar, we had an axis like this. We considered a small element like this here. Then we said such elements can occur between this, from this side to this side, because if I take different elements will be at different distances from the rod. അപ്പോൾ ഇവിടെ ഒരു എലിമെന്റ് എടുത്താൽ ഇത് ഇത്രയും ദൂരെയാണ്, അടുത്തൊരു എലിമെന്റ് എടുത്താൽ ഇവിടെ ആയിരിക്കും, അടുത്തൊരു എലിമെന്റ് എടുത്തിവിടെ ക്ലോസ് ആണ്, ഇത്. If I consider different elements on this body, they will be at different distances from the axis. That is why I want to integrate. അപ്പോൾ integrate ചെയ്യുമ്പോൾ മുമ്പേ ചെയ്ത പോലെ -l/2 to +l/2. This strips or these small sections or elements can lie on the scale. That is why we are integrating from this point to this point to get the result. So now what is the condition here? Here you can see that whatever be the element എവിടെയാണെങ്കിലും this will be at the same distance from the axis, because I am considering an axis like this which is passing through the center. ഞാൻ ഈ റിങ്ങിന്റെ ഏത് എലിമെന്റ് കൺസിഡർ ചെയ്താലും it will be at the same distance from the axis, and that same distance will be the radius of the ring. അപ്പോൾ ഇവിടെ ഇന്റഗ്രേറ്റ് ചെയ്യേണ്ട ആവശ്യമില്ല. Just what we have to do is just to sum. I have taken the moment of inertia of the particle of mass m, small element. What I have to do is just sum up. No need of integration, because all the particles in the ring, they are situated at the same distance from the axis we are considering. So what we have the next step? The next step will be, therefore, mi of the ring about p2 is equal to sigma m r squared. So the logic here is that this ring is made up of all such elements. So sigma m, what is sigma m? Sigma m means we are considering this small element, the total mass of all such elements. Total mass of all such elements in the ring will be nothing but capital M, where M is the total mass of the ring. So that is M is the mass of the ring. So sigma m is equal to m. So the adding up all the masses of all the elements which is forming the constituting the ring, that will be m, and this will be r squared. So I can write, therefore I can write this to be I, that is I is equal, taking this here, I is equal to m r squared. So this is the expression for the moment of inertia of a ring. So if I have a ring like this of mass capital M and radius capital R, the moment of inertia of this ring about an axis which is passing through this one, this axis will be mr squared. So there will be problems like this. You will be given the mass of this ring, radius of the ring will be given. You will be asked to find out the moment of inertia of this ring about this one. This will be mr squared. Okay. Now we are going to change the axis, just like we did in the case of uniform bar. Now we have taken axis to be here. What will be the case if I am taking another axis like this? I have considered this, I have got this to be mr squared. If I am taking another axis like this, what will be the moment of inertia of the same body about this axis? If I am taking an axis like this or this, that means, hope you know what I am making. I know this one, okay? I know this one. What about the moment of inertia about this one? If the ring is rotating like this, what is the moment of inertia about this one? This one we have found out to be mr squared by, so I mean mr squared. What about moment of inertia about this axis? What about moment of inertia about this one? Also, what is the moment of inertia if I am considering an axis like this? The ring can rotate like this. I mean, the ring can rotate like this also. About this axis, okay? About this axis, the ring can rotate like this also, okay? If there is a rotation like this, it will be an axis which is lying in its plane. Now we have considered this axis about which the ring will be rotating like this. If I am considering another axis which is perpendicular to the earlier axis, it will be rotating like this. Then what will be the moment of inertia? So there it is there that we are going to make use of another theorem we have already studied, that is perpendicular axis theorem. If I know this moment of inertia of the body about this axis, I can find out the moment of inertia about this axis, because this axis and this axis are perpendicular. So then there we have to make use of the perpendicular axis theorem. That means the moment of inertia of this body about this axis is the sum of moment of inertia about this axis plus this axis, if I am considering two perpendicular axes. So that is the next topic. Okay. Now the next derivation is to find out the moment of inertia of the same ring about a particular diameter. So it is like this. As I already told you, we have already found out this one, moment of inertia of this ring about this one. Now we have to find out about any diameter. Diameter means this is in the plane of the ring. Here this one or this one. So this can be a diameter of the ring. This can be a diameter of the ring. Now we know only this one. Okay. So how will you apply this? This is by making use of what we have already studied, the theorem of perpendicular axis. What is theorem of perpendicular axis? If I have a lamina like this, just for recollecting what we have already done, we have an z axis here, x, y. So these are all mutually perpendicular axes. If the moment of inertia about of this body about this axis is iz, this about this axis is ix, about this axis is iy, I can write this iz to be ix plus iy. So if you take two mutually perpendicular axes, moment of inertia of the body about this axis plus this axis will give you the moment of inertia of the body about the perpendicular axis. This theorem we have already studied, and this is called the perpendicular axis theorem. Now we can make use of this theorem here. Now the situation is similar to this one. I have taking two mutually perpendicular diameters of this ring. Let it be AB and CD. Two diameter just like this. I am considering one like this, one like this. Okay. So if I am taking the moment of inertia about AB, moment of inertia about CD, they will be same because they are mutually perpendicular, one diameter. So they will be same. So I can write here. What I can write here is that applying perpendicular axis theorem, what I can write is moment of inertia of the ring about this perpendicular axis is equal to moment of inertia of the ring about AB plus moment of inertia about CD. That is what perpendicular axis theorem states. So that we will first write here. Mi of the ring about PQ is equal to Mi of the ring about AB plus Mi of the ring about CD. Okay, so this is what is implied in the perpendicular axis theorem. Okay, so now this we have already found out. What is that? This we have already found out as MR square, and also we can note that Mi of the ring about AB is equal to Mi of the ring about CD. And these are same because they are two mutually perpendicular diameter, രണ്ട് diameters are. So let it be I. Okay, this is also I, we are taking it to be I, this is also I. So if you sum I plus I, you should be getting this one. The moment of inertia of the ring about PQ, we have already found out that it is mr square. So I can write this here. Mr square is equal to, I have taken each of this thing to be I. So that will be I plus I. That is equal to 2I. And this I is equal to mr squared by 2. So this is what we are getting. So remember that when I consider a ring about PQ, that is ഇങ്ങനത്തെ axis, ഈ ഒരു axis, this axis I considered first. About this axis, the moment of inertia of the ring was mr squared. Now I am calculating about this axis as well as another mutually perpendicular axis in the plane of the ring. നേരത്തെ perpendicular to ring ആയിരുന്നു, passing through the center. Now we have two diameters, one is like this, one is like this. So this moment of inertia about this plus moment of inertia about this will give you moment of inertia about this. So this will be, we already studied to be mr squared. About this will be mr squared by 2. About this will be mr squared by 2. Mr squared by 2 plus mr squared by 2 will give you mr squared. So this is where you apply the principle of, or the theorem of perpendicular axis to find out the moment of inertia of a body about other axis. If you know the moment of inertia of the body about a particular axis. Okay, just like parallel axis theorem, we have perpendicular axis theorem to find out the moment of inertia of the bodies about other axis. Given we know that, provided we know the moment of inertia of the body about a given axis. Okay, next one we will consider another axis. ഇപ്പോൾ നമ്മൾ കൺസിഡർ ചെയ്തത് ഇതാണ്. Just like if I am considering one like this, what will happen? Just like this. So I have considered this one and this one and this one in the plane of this one. What about this one? I have an axis here. We have already derived it to be mr squared. Now I am taking another axis like this or this. Okay, so about a tangent, this is a circular one. No, what will be the moment of inertia about this one? So a lot of things you can find out. If I know this one, I can find out this one by applying parallel axis theorem. Okay, if I know this one, I can find out this one by perpendicular axis theorem. അപ്പോൾ അങ്ങനെ ഈ രണ്ട് തിയറം ഉപയോഗിച്ചുകൊണ്ട് we can find out others. Now what we are going to find out is the moment of inertia of the ring about an axis passing through the tangent. Okay. Now we have another axis, a third axis that we are considering, that is about a tangent in the plane, like this. Okay, like this. Okay, so whatever we know is moment of inertia of this ring about PQ, we have already found out to be mr squared. Okay, about this diameter we have found out to be mr squared by 2. This is what we know. അപ്പോൾ നമുക്ക് ഈ perpendicular axis ഉള്ള mr squared, the about this diameter we have already determined to be mr squared by 2. Now we have to find out about this one. Now we can note immediately that these are parallel axes. This is an axis passing through the center. If I know this one, I can calculate the moment of inertia about this one. Just apply parallel axis theorem. So what is parallel axis theorem? Parallel axis theorem is moment of inertia about this axis is equal to moment of inertia about this axis plus the product of mass and square of the distance between this axis and this axis. So immediately you can write this, the distance between this axis and this axis is nothing but the radius. Radius will be the distance between this axis and this axis. So I can write the moment of inertia about EF will be equal to MI about EF is equal to MI about CD plus mass of the ring. Mass of the ring I have already taken to be capital M into the square of the distance between these two. That will be the square of the radius of the ring itself. So this will be the result. Mi about CD that we have got as mr squared by 2. That is mr squared by 2 plus mr squared. This is nothing but 3 by 2 mr squared. So if I am taking this as I is equal to 3 by 2 mr squared. So this is what we are going to get. So now we have taken three axes. One was the perpendicular one. About this one it is mr squared. About this one it is mr squared. About this one it is 3 by 2 mr squared. Now what about that is not in the syllabus, but we can consider another axis. Suppose we have an axis like this. Then how will you find out? I mean, we have taken this axis earlier. The first case was this axis. Now we consider this one later. Then we consider this one. Now we consider this one. Okay. So from this, you can find out this, because these are two parallel axes. Okay. That is perpendicular to the plane. Perpendicular to the plane through the center. Perpendicular to the plane through the side. Okay. This, from this you can find out this again by applying parallel axis theorem. If you want you can determine. So how will you determine that? We know this one. So it is just like this. We know this one. This is mr squared. Now we want to find out this one through about another parallel axis. This will be, and that is equal to apply parallel axis theorem. Know that this distance is r. About this axis will be, this is PQ, we have already studied, taken. I is equal to mr squared plus parallel axis theorem, that mr squared. Okay, this will be 2 mr squared. Okay, this one, about this one. So to sum it up, mr squared. Okay, about this axis it is mr squared. About this axis is mr squared by 2. About this diameter mr squared by 2. 3 by 2 mr squared. Again mr squared. And what about this axis? It is 2 mr squared. Right? 2 mr squared. So mr squared by 2, mr squared by 2, 2 mr squared. Okay. So in this way, if you know the moment of inertia about any axis, you can find out other axis, making use of parallel axis theorem and perpendicular axis theorem. So that is all for today. In the next class, we will see other bodies, like we have a thin circular disc, then we have a cylinder, then we can have a solid cylinder, a hollow cylinder, like that. Then at last we have a sphere. അപ്പോൾ അതിലും പല ആക്സസ് നമ്മൾ കൺസിഡർ ചെയ്യും. ഡിസ്ക് ആകുമ്പോൾ അങ്ങനെ എന്തൊക്കെ കൺസിഡർ ചെയ്യാം. ഡിസ്ക് ആണെങ്കിലും ഐ ക്യാൻ കൺസിഡർ ആൻ ആക്സിസ് ലൈക്ക് ദിസ്, ഐ ക്യാൻ കൺസിഡർ ആൻ ആക്സിസ് ലൈക്ക് ദിസ്, ഐ ക്യാൻ കൺസിഡർ ആൻ ആക്സിസ് ലൈക്ക് ദിസ് ഇൻ ദ പ്ലെയിൻ ഓഫ് ദി ഡിസ്ക്, ലൈക്ക് ദിസ്. Okay, different axes I can consider, and I can calculate the moment of inertia using parallel axis theorem and perpendicular axis theorem. Okay, thank you.